The broadcast is now starting. All attendees are in listen-only mode.
I am still audible, right?
Yes, we can hear you.
Okay. Uh,
Slideshow is not visible.
So I think Satyajit Das can't hear us.
okay, so the broadcast has been started, right? Am I audible now?
Yes, yes, you are. You are, sir.
Okay, okay. Well, we can start the recording now, I think. Yeah. Have we started the broadcast?
Yes, yes, sir. We have started it.
Okay, okay. Sorry. Okay. Good evening, everybody. Welcome to the 13th lecture. So today we will start with TensorFlow. We have already covered the lectures for the PyTorch. So in PyTorch, we have defined one model, we have trained that model, we have accelerated the training. Now in the TensorFlow also, we will do the same things, but there are some purpose to learn TensorFlow. There will be some advantages, some disadvantages also, but TensorFlow will give you some flexibility in terms of some acceleration in distributed training and so all these things we will see. But before going into the TensorFlow part, we would like to mention that
Excuse me, sir.
yes,
Sir, your slides are not visible.
okay. So my screen is visible, it seems. Visible now?
Yes, sir. It's now visible.
Okay, okay. Okay, so we will start with TensorFlow versions because it is very, very important to understand that if you are coming from TensorFlow 1 and there are TensorFlow 2 versions, several versions are available. So these two versions programming or approach is kind of different. So earlier 2019, we used to use TensorFlow 1 heavily. And after the release of TensorFlow 2 Alpha, the most common practices of TensorFlow 1 has been disseminated, and we have now new paradigm of programming in TensorFlow 2 and subsequent versions. So as we have, you can see in this slide that there are more than 1,800 contributors worldwide. And of course, it's Apache 2 license that is open source, and it was released in 2015 as TensorFlow 1, and several series came up after that for TensorFlow 1. So TensorFlow 1 was heavily based on making graphs and then introducing the lazy execution of the graphs, which mostly if you have followed the distributed programming of Spark, that is kind of same program paradigm. But in TensorFlow 2, that program paradigm of lazy execution has been transferred to your eager execution. Okay, so eager execution means as soon as you define something or any operation you define, it will be evaluated in instant. Right? So that is completely opposite of your lazy execution that was followed in TensorFlow 1 and subsequent versions. So from the TensorFlow 2, we have eager execution, and from the structural point of view, TensorFlow 1 was a bit difficult to follow if you are coming from completely Python background. And TensorFlow 2 is more a Pythonic approach, and it can be very suitable for beginners to experts, because different levels of programming is there which you can follow to define your particular model that you want to train. Now, so if you see the structure or architecture of TensorFlow, so basically the TensorFlow architecture has three main blocks. One is the training block, another is the save and repository block. In the middle, you can see here. And the right hand side, you can see the deployment block. So all these three blocks, which have been introduced in 2.0 and subsequent versions, this made the life much easier for the development and deployment of deep learning algorithms seamlessly. Okay. So in the training module, you'll see that we have distributed training strategy core, so which is written in C++, and that supports CPU, GPU, TPU execution, and of course multi-node CPU, multi-node GPU, multi-node TPU. So all these kind of combinations that supports. And for defining the model itself, you have high-level APIs as keras and estimators, but it is recommended that you don't use estimators nowadays. Keras implemented from TensorFlow. So keras has two implementations. One is native implementation. So if you are using keras IO, and there is another implementation from TensorFlow itself, and which we will use for defining our models. And most of the TF2 or TensorFlow 2 versions are very, very compatible and efficient with this high-level API defined by the keras. Now we also have data design modules as tf.data and tf datasets. So now this data design in TensorFlow is a bit different from that you have seen in PyTorch in the previous sections. So that also we will talk about, and there are much more flexibility in terms of data access, because the data sets, all the necessary modules that are actually designed by the TensorFlow designers itself. So all the data that are imported by this tf.data will have the flexibility to directly convert into tensors, which is the main data structure in TensorFlow, and use it subsequently. So in the entire pipeline, you do not need to convert it into the tensors and deliver to your GPU or TPU, right? So in terms of flexibility, this tf.data adds one more level of flexibility and efficiency while you are accessing data. There is this analysis or visualization tool, which is also available in PyTorch plugin that we have seen so far in the previous classes. And also here also TensorBoard is available with TensorFlow. TensorBoard is available with TensorFlow packages. Now for the saving model, we have the serialization saving model, so where you can save your model instantly and reuse it. And also there is TensorFlow Hub. So TensorFlow Hub is model repository. So if you want to use already trained models, which are already trained with defined parameters, you can use those parameters, you can tune them in your training, depending on the target model that you are targeting and the target problem that you are targeting. So basically, if you are targeting classification problem, depending on the number of classes that is available, you can tune the already existing parameters from the TensorFlow Hub. Now, the deployment part is completely giving the TensorFlow a new dimension. So the models that you have defined or trained or designed inside the TensorFlow modules, you can seamlessly convert it or deploy it onto your cloud based on browser. So if you are using browser, you can deploy browser with using TensorFlow.js. If you are trying to deploy your models for Android devices or iOS devices or Raspberry Pi, or even Android Arduino support it has with TensorFlow Lite Micro. So TensorFlow Lite and TensorFlow Lite Micro will have you need to use just to save just to use your saved models and convert to the targeted ways. Now, for the target cloud platform, you can use TensorFlow Serving, right? So all these deployment strategies are inbuilt. So different strategies there are, and we will see how to use them. So all these three stacks make actually the TensorFlow a bit flexible and flexible for product development and product oriented projects, right? So now the workflow is similar to that of your PyTorch. So you have to feature your data and feature engineer your data, transform or whatever you want to normalize your data. So all these things you will do in the beginning, and then you have to define the model, build the model. So as I was mentioning that you can use Keras pre-made estimators. So these estimators, as I was mentioning, that it is not recommended for the newer versions of TensorFlow 2. After TensorFlow 2.5, actually it is not recommended. And also you can use some APIs to custom build your models. So Keras is having all the models, mostly 90% of the models that are necessary to build your models. And if you want to go a bit more flexible and to have more control over model building, you can use these custom models building APIs, right? And then in the training stage of this pipeline, you have this eager execution as well as autographs. So this autograph will give you the efficiency of the graph-based approaches of TensorFlow 1. Okay, so once one way you have the eager execution, which is actually the instant evaluation. So in compile time itself, you will see what kind of errors are there, and you can evaluate your model depending on the definition that you have defined. And you can use autograph to enhance the performance of the model in the subsequent runs. Okay? So we will see how to define all these explicit APIs to be used to enhance the efficiency. Distribution strategy, as I was mentioning, that distribution strategy was written in core C++, and that gives it much more flexibility in terms of distributing the data parallelism, the model parallelism, as well as the pipeline parallelism. And of course, TensorBoard is inbuilt tool which you will use for visualize and analyze your model and give it much more boost in the subsequent runs. And in the end, you save the model and use it for deployment, right? So as I was mentioning that why we are actually moving towards the 2.x version is that the Keras, which is the newer implementation from the TensorFlow, and the eager execution. And this eager execution is highly efficient from the Pythonic approach of programming. So in PyTorch you have seen some, and in TensorFlow 2 and subsequent versions we will see much more of that eager execution. So this is just to have a look of the entire model that you have defined in compile time, right? And also robust model deployment. So deployment, that third stack you have seen, it is actually giving you the extra boost to use it over PyTorch. Okay? Powerful experimentation for research. So for researchers, there is some custom APIs that they can use to build or define the models from the scratch itself. So that is also similar to PyTorch. So whatever we have seen, that we will discuss in the subsequent slides. Now you have this deprecation of APIs, because many of the APIs that if you are coming from your TensorFlow 1 code to your TensorFlow 2 code, many of the APIs have been deprecated, and cleaning or clean up your code is very easy with cleaning up APIs. And TF.data, as I was mentioning, that loading data is giving another dimension, because there are many APIs in TF which is defined to distribute the data of which you are loading, to have prefetching options, to have pipeline parallelism options, also to have cache options, whether you want to store your prefetched data into your RAM or your disk. So all these APIs are already built into TF.data. TF.keras, that I just mentioned, that you can build the models with Keras API, high-level API. TensorFlow Hub, which is the already saved already saved models and parameters that you can get from. Also, run and debug with eager execution. Debugging also is very much possible with some one or two lines of code addition. Now, as I was mentioning, that it is highly efficient to run in CPUs, GPUs, TPUs, and distribution strategies is it's much more flexible, and you can customize the distribution strategy. We'll spend I think maybe 50% of the time in the next class to discuss this distribution strategy. Okay? And exporting saved models, usually this will help you to deploy efficiently using TensorFlow.js or TensorFlow Lite or TensorFlow Lite Micro, depending on the target environment that you are targeting, right? And TensorFlow datasets, already it has numerous datasets that you want for your model training. Most of the problems targeting, if you are targeting, let's say, classification, you are targeting computer vision problems, NLP problems, even segmentation or multi-stage definition of, let's say, segmentation and captioning of videos. So different data sets are available to give you much more flexibility to use this TF.data APIs to be used with the data sets that is already available. So now we will come to the model building. So model building part, as I was mentioning, that is giving you the options to start with for beginners. So as you can see here, from the left side, you have the beginners to the experts on the right side. And for the beginners, defining simple models, okay, it is very easy to use sequential API. Okay? So there are several APIs that is available in TensorFlow, as I was mentioning, that it is to give you flexibility and control. So this API, if you are using sequential API, most of the models you can build with this sequential API, because this API has all the built-in layers, okay, that you can reuse and you can define, and you can use to define your simple models. Next stage, if you are, let's say, engineer with standard use cases and you want to use the built-in layers of functional API. So basically, if you see the sequential API will give you the platform to define one model which has one input and one output. Okay? Of course, that input and output is multidimensional. No need to mention that. But the functional API has the flexibility to, now you will see that the flexibility is increasing step by step in the APIs that we are going on the right side, right? So now it has the improved flexibility to add, of course, the built-in layers that you will use. But now you will have the option to define multiple inputs and multiple outputs. And also those inputs and outputs can be at several stages. You can merge them, you can use to branch them, or you can define your model using multiple inputs and outputs depending on which stage you are using them. So as you can see, sequential API, simple models for beginners, functional API for built-in layers you will use, but You can define the multiple inputs and outputs. Now, if you go to have much more control over this functional API, you can have functional API plus custom layers, plus custom metrics, plus custom losses. So metrics, losses, these are essentially very important or crucial parameters that you want to track while training your model, right? Now you can define custom metrics, which metrics you want to track. Most of the metrics that you will use, as we have seen in the last Catalyst class, so all the matrices were actually defined in that framework, as well as in TensorFlow 2.0, we'll have many metrics that is already available. You can define custom metrics as well, custom losses, and define custom layers used with functional API. So functional API is essentially call the layers as functions. So the entire sequential API will give you the stack of layers. So this is completely one data structure. In the functional API, you will have this the graph of the built-in layers, okay, and you can call them. Okay, so the layers are callable now. And in subclassing, this is completely relevant if you are coming from PyTorch. So subclassing is same as programming from scratch, whatever you have done in PyTorch. Okay. Now you can say that why we need functional API again, right? We can do it from scratch. We can either use for simple models with sequential API, then why we will need functional API? But functional API has much more to it than you are seeing here. Okay, so we will discuss how we can actually define one model in using functional API very, very efficiently, not going for sequential, and why you will not go for subclass. Now, this sequential way of defining, so there are two programming paradigms that is supported in TensorFlow that I mentioned in the first slide itself. So tensor is essentially the data structure, and the flow is essentially the graph, computational graph that you want to execute. Now, from TensorFlow 2, we have this symbolic API, so which is Keras sequential API that you will use to define, where your model is a graph of layers, and any graph you can compile will run. And TensorFlow helps you to debug by catching errors at compile time itself, because it is supporting the eager execution, not the lazy execution, which was in TensorFlow 1. Now, in the imperative API, so subclassing is imperative API. So this is kind of object-oriented programming style, defining your models and using it. So in that subclassing, your model is essentially converted into your Python bytecode, and you will have much more control over the models that you are defining. And since it is completely customized according to your requirement, it is a bit difficult to debug, but of course, if you know the ways to debug, it is not that hard. Now the training part. So model defining, as you have seen, there are 4 kind of approaches or ways you can define it. And training the model also is kind of tricky if you are coming from PyTorch. So model.fit, this function is for quick experiment. You just call the forward function and it will do automatic gradient descent, calculating the gradients, updating the weight parameters and biases. So all these things will be completely automated. Just call the fit model over the model, or fit function over the model, that's it. Now callbacks. So callbacks you have seen in the previous class also in the catalyst. So that same notion is also here. You can use callbacks. You can customize your training loop by adding checkpoints, early stopping. You can have tensor board monitoring, Slack notifications. So this is quite interesting. You can define your model. You can now start the training, hit the training with callbacks. You can define one callback, which will give you Slack notification for each, let's say, epoch done. Okay, so for each epoch, what is the metric status or status of your training, it will give you notification. So you can all add all these callbacks inside here. So you can see model.fit is just simple way of training, the vanilla way of training, or maybe automated, completely automated. In the callbacks, you can add checkpointing, early stopping. So all these customizations you can add. Now model.train on batch, so this method plus callbacks. So you can now customize the training loop also. So customizing training loop with train on batch, because training loop has several options. Batch, optimizers, which loss function you are using. So all these are actually automated here in this fit functions. Train on batch plus callbacks, if you use, you can customize your optimizer, you can customize your losses, you can customize your entire training loop actually, and completely scratch development of your training loop also you can do with custom training. So here with gradient tape, so this is a very simple API which keeps track of all the parameters which are differentiable. Okay, so using this gradient tape, we will see how to program with gradient tape. So we're using gradient tape, you can customize or completely write your training module or training loop from scratch. So optimizations, modifying gradients, how you want to define your loss function. So loss function, as I was mentioning, so different loss functions are there. MHC loss, cross entropy loss, right? Now, if you want to define your own loss function, you can use custom training loop with gradient tape, where you can define your functions for your loss functions, and you can call that function inside gradient tape to be accounted for your optimizing. Now, as this is the basic of TensorFlow, so tensor data type. So tensor data type is, you have seen also in PyTorch, tensor's definition of tensors, right? But tensors in TensorFlow is similar. It has few features different from PyTorch tensors, but it is completely same as your NumPy. It is exactly same. However, you have defined your multidimensional simple single dimensional array in NumPy. It is the same way of definition, same way of function calling, same way of slicing. So everything you can use exactly same in TensorFlow. So tensor data type has a name and type and a rank. So type is essentially the data type. Rank is essentially how many elements it has, and a shape. So the name identifies uniquely the object which you want to use in your computational graph. So computational graph means, so if you recall the computational graph from the first PyTorch class, you have, let's say, a tensor, you have let's say weight tensor W, you have your tensor input as X. So W into X if you are doing, so that is one flow of operation. So this data is fed into the multiplication operation. So that is simple flow of data. And this flow of data is represented in computational graph. Now in computational graph, if you have what kind of data type you are using as tensors. So these are tensors, the input tensor, the weight tensor, the bias tensor. So all these are tensors, and what data type you are using there. Now it has lot of support for data. There's float 32, int 8, int 32, float 16. You can look into TensorFlow's website, tensorflow.org, to get more of these data types. What are the data types that are available, and how you can define your tensors for a particular data type. Rank is simply the number of dimensions of the tensor. So basically, scalar means it has one element, so rank is 0. Vector has rank 1, so basically one dimension it has, right? The shape is the number of elements in each dimension. So So let's say rank 2 tensor. So 2 dimensions are there. Now in each dimension, how many elements will be there? So that will be defined by the shape. So let's say a vector of shape D0. So basically D0 is the number of elements. Matrix of shape D0, D1. So D0 is the elements, number of elements in the first dimension, maybe row and column, let's say D1. So how many elements? So as simple as that. And the dimensions none. So there can be none also as dimension. Okay? And none is allowed and it indicates unknown dimension. Because in some of the programming of models, you will be using some tensors where you do not know how many batches will come or how many output of in particular dimension. For first dimension, how many elements will be given as output. So you do not know in let's say defining time of your model. You can use none in those places. Okay, next we will see the different types of tensors. So there are some immutable tensors, there are mutable tensors. So immutable tensors means you cannot change their values like constants. So tf.constants will be used to define constant tensors. You can define variable tensors, but remember that tf.variable which you are defining, but v is capital V. This is just the notion that TensorFlow uses, but for the constants, C is small. So variables, the data that you are defining tensor as, you can change their values. Okay. But most of the trainings, you do not need to worry about that. You do not need to define your tensors as low level as variable or constants. If you are starting with sequential or even functional level, if you are defining your tensors from scratch without using your TensorFlow data type tf.data, you can use these variable definitions for constants and variables. But most of the time you will not use them. Okay, but it is nice to know. And now this tf.data, as I was mentioning, that tf.data is much more flexible in terms of data loading and how it is. So we'll just see a few examples then, because this is just to show you the flexibility, how to define that. But we will use them explicitly and define how to define your TensorFlow data sets, TensorFlow data loaders, which actually storing the data, not such data loaders that you have seen in PyTorch. Now, Keras dataset you can use. Also, you can use TensorFlow datasets. So I mentioned that Keras has its own implementation and Keras has its TensorFlow implementation. In our cases, we will use Keras TensorFlow implementation. And of course, Keras TensorFlow, TensorFlow.keras has lots of datasets available. Now, if you are importing datasets from Keras, it is different if you are importing datasets from TensorFlow datasets. So tf.data. So tfds, if you are using tfds, that is different. And if you are using Keras dataset, that is different, because TensorFlow datasets are already tensors. You do not need to convert them or transfer them for your GPU or TPU which you are using. And for your Keras datasets, it is not the tensors. Actually, they will be imported as datasets as arrays or NumPy data structures. Now, if you are using TensorFlow datasets, you will have the flexibility to define the flag in memory true or false, because TFDS can load your data into your memory, into your RAM, to give you much more easy and faster access, okay, to the data. Let's say you are trying your data to be processed by CPU, and if you are using Keras dataset, then you are actually defining to be stored into the disk. You then load into the RAM, and here you directly load into the RAM as tensors, and you there you go. Okay. You can cache as well by using .cache function. Now cache, you can cache your data set which you are mapping for your let's say for this pre-process function. So let's say I want some images, some image classification problem I'm trying to address, where I need to pre-process the image data before applying them into the models. Now these pre-process function will be used several times depending on the number of batches or number of images that you are using inside your model. Now, if you are having this pre-process inside, I don't know where, you need to access that many times, you need to call them, right? Now you have the flexibility to cache it inside RAM or disk, depending on, let's say you are trying to cache anything as file inside your disk or cache anything inside your RAM, you can do that. And here we are using map function to actually map this preprocess with this many number of parallel calls with cached version inside your RAM, okay, directly. So that is also possible with ImageDS, which is the tf.dataset, right? Now we will go into the demo where we will see some of the concepts for tensor data. Okay, so tensor data we have seen, right? Now, how we can define the tensor data and how we can use different functions that is as similar to your NumPy functions, that is similar. So we will use Colab. Okay, I hope you are seeing the window for browser. So here we are using Colab to run this previous, let's say, TensorFlow 1. Now, to use TensorFlow, you just need to import. So if you are using local machine, you need to install TensorFlow and you need to check which versions you are using. So TensorFlow version is very, very important to confirm so that you are not using TensorFlow 1. And here in all the tutorials, demo sessions, we will use TensorFlow 2.x, any versions after 2. Okay, that is fine. So if you are using your local machine, you should ensure that you are using TensorFlow version greater than 2.0. Now tensors, as I was mentioning, defining tensors is very easy. So basically, this is a string tensor, which we are defining as variables, right? Now this is a single dimensional scalar with rank 0 string, okay? And this number is again another rank 0 tensor, which is again a variable, floating variable. Now you can see that tf.data type you can use, okay? And several data types you are using. Now, these data types is very important in model training, because in the previous class also we have seen that with mixed precision training, we can enhance or improve the performance manifold, and using different types of data and exploring your design model is very, very important to see how you are improving your performance, both performance and how it affects your accuracy. Now rank, as I was mentioning, that if you want to see the rank, let's say I want to see this TensorFlow rank. So basically, this is a single dimension, and this is 2-dimensional, right? So the rank of rank 2 tensor is basically NumPy 2. Okay, so 2 rank. So this is the 2-dimensional tensor. So you have 2 rank. And shape of the tensor, so it's rank 2 dot shape. Now 2 rank means it has 2 dimensions, and in each dimension you have 2 elements. So 2 by 2 is essentially your shape, right? So understanding shape of the tensors and rank of the tensors, these two are very important, because to compile the model that you have defined, you will get different shape and ranks of the tensors. So rank is essentially how many dimensions are there. So let's say if you are training the model using batch, so how many batches you are using in each layer, that will come as rank. Okay, and the shape, then how many elements in each dimension, so that is the shape that will. Now changing the shape, we can use reshape method to actually change the shape. So here we have this once created shape as 1, 2, 3, right? So all the elements in this tensor is essentially ones. Now I want to reshape this 1, 2, 3 to 2, 3, 1. Okay, so tensor reshape, and tensor 3 is reshaping to 3 minus 1. So minus 1 is telling you how many elements will be there automatically in this dimension. So here in the first dimension we have 1, second dimension we have 2, third dimension we have 3, first 2, 3, 1. Here we are saying first dimension we have 3 elements, and in the second dimension we do not know, infer it from the reshape. Okay, so same minus 1 you have used before in Python. So printing this, the tensor 1, tensor 2, tensor 3, that is the different tensors that you have initialized. So you can see 1, 2, 3 shape, right? Completely one element 1, 2, 3. Tensor, the second tensor was actually 2, 3, 1, right? So 3 and 2, so 2 total of elements and 3 elements in these 2 elements, and total of 3 elements and 1 actually element in each dimension, right? So 1 element in each dimension. Now in the third, you can see that that shape already taken as 2 because we had minus 1. So it will automatically compute how many elements will be the second dimension. So this is basically 3 rows and 2 columns matrix. Slicing tensors. So this is also important if you are using different data types in different shapes. So basically here we have defined one 2D tensor, and then we are actually selecting, let's say, third element from the first row, selecting the first row completely, selecting the first column, selecting the second and fourth column, and printing all the column values here, and then we are selecting column in one in row 2 and 3. So column 1 in row 2 and 3. So basically column 1 from 2 and 3. Okay. So this is the column 1 value 0, and from 1 to 2. So basically 0, 1, 2. So basically 2 and 3 row you are accessing. So basically, if you see the outputs, you will see the tensors, whatever tensors you have got. So first we are accessing the element from third element, which was 3, right? So 3, and then you are accessing the first row, then the first column, then the second and fourth row, and then the first column in row 2 and row 3, right? So this is the first column in row 2 and row 3. And you can see the shapes and different data types that are being used. Okay. Now different types of tensors are there: variable, constants, sparse tensor, and placeholder. Placeholder is not recommended also in the 2.x versions. So you can go to this link to see more of this usage of tensors. So this is just few basics that I wanted to cover for the tensors, because these tensors we will use almost in all the layers that we want to define in the model. Right? Now coming to the model. So what we have told that you can define your models by using sequential API, you can use functional API, plus. So basically customized callbacks, your customized optimizers, and so on, and then subclassing. And in this tutorial, we will see the usage of Keras API with sequential paradigm. Right? So importing the necessary versions. So now percentage TensorFlow version 2.x, this comment is necessary if you have multiple versions available inside your system for TensorFlow, and it will actually force to use the 2.x version level. We are just importing then the Keras, the API functional API, the Keras high-level API from TensorFlow. We are not using the TensorFlow, the Keras IO library, which is the native Keras. We are not using. We are using TensorFlow. Helper libraries from NumPy and matplotlib just to work with arrays and plotting. Now in the data set, you can see we are using Keras data set here, okay, not the TensorFlow data set. So all these things you should keep in mind while you are programming or doing the model definition, because most of the students or researchers I have seen that they just copy some code from somewhere else, but they do not know what kind of pipelines that are being used, because TensorFlow has several options, several combinations, several compositions of different APIs. So if you're not aware of which API you are using, you will not be able to accelerate your train. So that is why here we are using Keras, just keeping in mind, okay, just because to be sure that we are just extracting, unpacking the training images labels and test images labels from the fashion MNIST dataset, that dataset you have seen also previously. And we are using dot shape attribute to see how many images that training images have, right? So after downloading, so basically we have downloaded everything. Now you can see that 6,000, that is the number of samples that is available, 28 by 28. So you can see the correspondence with the NumPy. Okay. So we have got 60,000 images. So train images just to see what is there in, let's say, 23 by 23 pixel of the first image. You can see 194. So the values here actually varies from 0 to 255. So basically what is to be done to be pre-processing, in the pre-processing part, you just need to normalize it with 255. So that is what we are doing here. The same thing you have seen in the data loader for the Python PyTorch for the training sets and test sets pre-processing of the data. Class names, we are extracting and saying that these many classes will be there, and these are the names of different classes, right? We have extracted the models. Now data pre-processing part is essentially just normalizing. Okay? Now again, all these operations are happening inside your CPU, okay? And we are using simple NumPy arrays and NumPy operations. Okay, so simple math that is operated on the array. Okay. Building models. So now we will try to build the models. You can see that we are using keras.sequential API, sequential API for beginners, and all the models, model layers, what are defined for. Let's say you are targeting classification problem, you are targeting LNP problem, as I mentioned. So there are numerous numbers of layers that is already defined in Keras. So Keras TensorFlow, you go to that website for Keras TensorFlow and see how many layers that is already available in the sequential API. So as layers, we are using flatten layer and dense layer. Flatten is essentially the helper function to flatten your input array. Okay, so this is exactly the input layer. So in the PyTorch also, so every time you will just need to see the equivalence in the PyTorch. Okay, so you just visualize whatever we have seen so far and what we are seeing in further classes. So in the dense layer, so this is the dense layer. Basically, this is the fully connected dense layer or linear layer that you have seen so far. Right? So again, I am mentioning that you go to Keras sequential API and see what are the layers available. Output tensor dimensions. So 10 is the output number of neurons that I want from this dense layer, because 10 classes are there. And activation, ReLU, again, all are predefined. Activation, softmax. So basically, we are just defining these layers. So dense layer. So it will take whatever you are giving input from here and give output as 128 neurons with this activation. And then we will have the second dense layer, so two-layer definition model that we are defining here. And you can see in the output we are having 10 classes here. So this is just as simple of definition of model. And there is nothing else you need to do. This is very simple sequential API. Definition of layer 1, 2, 3 that you can see here. But what is most important is that model.compile. Now, this is the eager execution. So when you are using this compile, then at this time itself, you are actually compiling your model. Without running the model, you are actually analyzing what are the attributes for the layers that you have defined. Is that correct or not? All the parameters that you have used for defining your layers. So I did not know. So if you are working elsewhere, if you are not using compile, then you are not essentially taking the efficiency of eager execution. As long as you have defined it and run it, the graph is already defined and evaluated for compile. So basically in the compile, we are seeing all the things that you have defined is correct or not, and compile time check you can do it. Then if you just, so everything is okay, there is no error, you can fit it for the training images and training labels for this many number of epochs. So you can see how easy it is to define one model training with, so defining layers with sequential API and training model with fit method that you have seen in the slides. So on what? Training images, train labels, and epoch. That's it. And it will train it. But before that, you have already checked your model is correct or not, right? And evaluating the model is, again, it is easy with evaluate method. Okay. So model.evaluate. So all the things we are doing here is sequential API, and we are not using subclassing or functional API. So we will see subclassing and functional API with the different data distribution strategy that are available in tf.data in the next class, but just get familiarized with the simple beginners APIs that are available with TF. So we'll go in advanced model definition in the coming class. So you should be aware of these simple models definition. Now printing the testing accuracy. So all this, so when you are actually calculating the evaluation, you are getting the tuple for the loss and accuracy, and you can print it. Okay. So this is all these are actually abstracted. You do not need to define anything. So basically, if you want to verbose the output or not, that also you can define. Now we can actually test that. So basically, testing accuracy that we have evaluated, but to test, you can call this predict method to get the predictions, and you can use these predictions. So basically, which prediction index has the highest prediction probability? That's it, right? So you can get it, right? Which is the argmax. Okay. Right. So now we want to verify the predictions. So basically, whether your 9th level is actually correct or not. So here is simple function. This is nothing to do with training or evaluating. So this is just we are checking whether the 9th level is fine or not, accessing the particular index. Okay, indexed image, okay. And you can go to these links for detailed definitions of or different optimizations that you can use in the TensorFlow and so on. You can also visit TensorFlow sequential API to see what are the flexibilities you can have, like how much you can go with the fit and predict and evaluate. Right? Now we will see a bit about how we can actually compute in GPU. So basically, this is a bit different from defining the device for in PyTorch and transferring the data into your GPU and model inside the GPU. Here, actually, you have much more flexibility in terms of accessing or offloading the tasks or pipeline of your training module inside your GPU. So that way, the distributed training of TensorFlow is much more efficient. So in this class, we'll just see how to define the GPU and then how to define the program codes which will go to your GPU or TPU rather, depending on the device you want to access, or CPU, I don't know. So here, accessing to your importing your module and then device name is essentially tf.test.gpu device name. So whether what kind of GPU is available, GPU 0. If not found, it will raise the error. So you just change the runtime type to GPU if you're using Colab, right? And if you have already in your local machine, if you have GPU, then well and good. So now in the TensorFlow, how we will offload the task, right? So basically, device name we have gathered, if whether it is a GPU or it is a CPU or it is a for the TPU, we have not written the code here, so we'll just see the CPU and GPU here. TPU maybe we'll see in the next class. Now for the CPU, so basically div CPU, this function I will run. So basically with tpu.tf.device, if it is CPU, then this segment of code I want to run. So what segment of code I am running here? Again, you can see that keras.layers.convolution2d. So this is again defined in keras.layers, and some input random image I'm creating with 100 batches of 100 by 100 into 3 channels. Okay, so this is the tensor dimension. Okay, so again the rank, the shape. Okay, so you just correlate to the idea of the tensors, that the predefined concept. So basically, this is giving the output of your convolution 2D of this random image. Okay. Again, this is what kind of layer that I will not tell you now, but this is just I'm running one layer of one model just to see whether it is running in CPU, and another layer we are defining here, made GPU, and that also we are running inside our GPU. Okay, so we'll call these two methods to run both in CPU and GPU. The same dimensions of inputs we are running here, and actually just to see what kind of achievement we are getting, we have called these two methods and printing the time taken by the two devices, right? So as you can see, we are getting 67 times just to simulate one layer only. Okay. So, but you can see, right? So defining functions with devices, like which device will run this piece of code. That flexibility is something that we'll exploit in distributed training. Okay. So basically, we'll distribute. Of course, there are several abstractions of the APIs. You may not exactly define like these functions, but this is giving you an idea that yes, we can customize our pipeline much more efficiently with what kind of device it will use. Let's say you have tensor processing unit available, GPU unit available, CPU available, multi-core CPU in multiple nodes. Now this is where we will see that whether this piece of code you want to run in GPU or this piece of code you want to run in TPU, right? And numerous examples will be there to exploit this distribution strategy. Of course, as I was mentioning, that there are several abstractions of these strategies that you can use directly without defining that this piece of code will go to this piece of device, but the strategies in underlying these are the techniques that will be used to actually distribute with different strategies that we will use. Okay, with this, we'll conclude today's session, and we'll jump to our question and answer. And thank you. Okay, so let me go towards the uh, tab here. So uh, okay, so questions I can see, but just one second. Most of them are answered already by. Okay, good. So let me see. So questions we have. Which version of Python is supported by TensorFlow 2.0? Yeah, this is. Yeah, so this is already answered. 3.7 to, yeah, this is good. We do not need here train and test split. Yes, so train and test split. Okay, so this is also answered. The code is for an understanding of CPU and GPU performance. Yes, but the test split that we have seen in PyTorch, of course, you can split your training and test dataset. Okay, 75-25, 75, 70-20-10 train validation test. So what kind of segregation you want to do, you can do it. Okay. Now, what are the other available metrics apart from accuracy? Lots of things are there depending on the problem that you are targeting. So let's say classification you are targeting, or segmentation you are targeting. So there will be precision, there will be recall, there will be, so all these are model model performance. Okay, and accuracy loss. So these two are the basic metrics. You can have F1 score. You can have we just saw in the previous class in Catalyst, right? So there are many metrics, confusion metrics you want to find in the end of your regression problem, right? So all these things you can do with these metrics. So different metrics are there. What is amazing? What was amazing? Oh, it was amazing lecture. Thank you. Okay, thank you so much. Difference between TensorFlow and Keras. These two are frameworks. You can think it of independent framework, because Keras native, which is actually the prior implementation. So TensorFlow 1 and Keras was actually parallel at that time. Then when TensorFlow 2 came, then the designers thought, why not put because Keras has Keras framework has many implementations already, which are very crucial to come up with this sequential API strongly, right? So that way TensorFlow adapted that Keras implementation, and now you can use both. So you can completely define your model with only Keras or TensorFlow Keras, depending on what kind of platform or framework you are targeting. What is the difference in execution strategy between PyTorch and TensorFlow? Execution strategy, again, the PyTorch execution is completely Python bytecode execution. Okay, so that is completely imperative. And in case of TensorFlow, you have both. Okay, so we have talked about that. You have both sequential, the eager execution, and you have imperative. Speed difference, by the way, Keras and TensorFlow dataset APIs. Speed difference. I did not understand this question. Can you please repeat? Next question is, does the TensorFlow data loader allow parallel fetching, preprocessing of data Yes, exactly. And that we'll see in the next class. Parallel fetching, prefetching actually uh, is prefetching with parallel fetching and caching, pipelining. So all these are very crucial to know if you are working with TensorFlow. So TF.data we will use in the next class for describing all these data accesses. Sequential API does it has single input, single output? Yes. Sequential API for training module definition, if you are using here's sequential API, then yes, it has single output. I mean, the way it is defined, it is single input, single output. Uh, now, if you want single input, there's a multiple output. You want to branch, then again concatenate, and then again you want to go in the final merged way, and again maybe branching. So depending on the problem approaching, if you want to use, let's say, multiple input, multiple outputs at different stages, you go for functional API. Functional API you will see tomorrow. I mean, in the next class. Case where we can use functional API. Yes. So let's say this is very good question. So let's say I am given one image, okay, and this image has two dogs. One is black one is brown one, right? So the VQA problem, visual and query question answer problem. So you want to classify. I want to ask, like, the dog on the right has which color? Okay. So this kind of problem, you need to process your text in one pipeline, and in another pipeline, you need to process the image itself to classify which dog we are talking about. On the right side, what dog is actually is it brown or is it black, right? And in the another pipeline, you need to process the question answer itself. So you can imagine that this kind of problem where you have multiple pipelines of getting the output in the end. So in the end, we'll concatenate, but we want to get the output as the right side dog is brown, right? Or the right side dog is not brown. So this output I want to get it, but to get this output I need to process these two pipelines. One pipeline is the image pipeline, another pipeline is natural language pipeline. So you can imagine, so two outputs will emerge into one single input to your last classification. So that way, multiple input, single output, so functionality. Okay. While training, we have explored in examples model.train, model and fit, any other model. Okay, so this is for your PyTorch and this is for your TensorFlow. Okay, fit is for TensorFlow. Does PyTorch give better performance than TensorFlow? If yes, why this is? This is good question. If you don't know how to develop your model efficiently in TensorFlow, you will get worse performance in TensorFlow compared to your PyTorch performance. Because in PyTorch, mostly you will be developing your model from scratch mostly. So subclassing you are doing here. Okay. In TensorFlow, which is called your subclassing. Now, in TensorFlow, there is functional API or an autograph. Now, if you are using autograph feature enabled in your program running, so you need to know how to accelerate, right? If you are using that, so I will not say which will give you better result. Okay, I will say which way you can get it better. Okay. So now in the TensorFlow, if you are using the autograph, after the first run, it knows that what graph you are actually training, right? Then it will optimize the computational graph itself and the performance will increase manifold in the subsequent runs you'll see. But that is not the case in Python. Okay? Keras.datasets and Keras.dataset are different or same. Keras.datasets, I think dataset, it is the okay, tf.keras.dataset. Okay. So tf.keras.dataset, that is the Keras TensorFlow dataset. If TensorFlow has kept all the same dataset as Keras native implementation, so then yes, it is the same. It is just how many data they have integrated. Okay, the performance wise, it is same. Okay. What is Linux command in command prompt to run .py training file? Just simple Python space your training file, right? .py. That is simple Python example. I mean, Python running command, Python file running command, or Python script run command. On less powerful edge devices, TF Lite is usually supported. Does TF Lite have any major differences compared to TF? Yes, indeed. There are many differences. So the mixed precision. So there are a lot of ways you can actually reduce or shrink your model if you're using TensorFlow Lite. There are many quantizations, there are many compressions that are available where you can compress your model while you are going for TensorFlow Lite implementation. But again, you need to check how much accuracy you are maybe getting reduced or sacrificing. So depending on that, you can deploy your model. But there are many other APIs that are available that can shrink your model to your TensorFlow. Model.compile, as mentioned, reflects eager execution as it runs step by step. Does it slow down the model execution? No. This is again eager execution. This is one-time run. That's it. No, it is just compiled your method, your model. That's it. It checked. You have checked everything is fine or not. That's it. So for the subsequent runs, you will not need to do the compile again, right? Okay, so in the next section, I cannot see any further questions. I think every questions have been answered, right? So yeah. Okay, so you go through the slides and the code sections that I will share the link from, and go to the TensorFlow.org website itself. And it is recommended that so TensorFlow website is very much designed to directly run your all the queries that you may have while implementation. All the pointers we are giving here, we cannot cover all the aspects of designing one model, but all the pointers which we are giving from here, you can use those while accessing or browsing your browsing for TensorFlow website itself. And there are many references, there are many source codes that is readily available. You can run readily with Colab or with GitLab or GitHub notebook. So that is completely free. So you can go there and explore more. With this, we'll close this session. Thank you all for all these interesting questions, and see you in the next class. Thank you.